Hey there, today we are going to talk about rational functions. Before we start diving into rational functions and specifically their graphs, we want to talk a little bit about notation, specifically arrow notation. Now, oftentimes I will see students use arrows to separate steps in solving an equation, when usually we really should be using an equal sign there. Because arrows have very specific meanings in math, and we try and use them sparingly just for those reasons. One of the reasons we might use an arrow is for indicating when one variable or value is approaching another value. So here in this section, we're going to be looking at the behavior of rational functions as they go off to the sides, either up and down or to left or right. And so we're going to use language like seeing what happens as x approaches some number a, or maybe f of x. If I use a plus there in the notation where like an exponent would go on the a, then that means I'm approaching the number a from the right side. So from my right going in a negative direction. If I put a negative there where the a would have an exponent normally, then that means I'm approaching a from the left side. So coming from the left and heading in a positive direction. So whenever you see an arrow, when we're talking about graphs and behavior, it usually means that we're approaching something. So let's look at an example. Here we've got the function 1 over x squared, and we're going to look at its behavior at the ends of the graph. Right? So what happens as it goes up in the middle there, as we see, and what happens as it goes off to the right and left. And we want to be able to read this notation so we don't have to write out long sentences explaining this kind of stuff. So our first question asks, what happens to f of x, so the function, as x approaches 0 from the left? That's how I would read that. If you've got x, arrow, 0 with a negative, where the exponent would normally go, and the superscript there. So that's x as, what happens as x approaches 0 from the left? So that means I'm looking along the x-axis, because x is approaching something, and I'm coming from the left side of the graph, so the negative side of the graph, and I'm approaching 0. And we can see as that happens, the graph shoots up very dramatically and is heading off towards infinity. Now, it's never actually going to hit 0 because I can't plug 0 into this function. And so that's why we talk about what it's doing as it approaches 0, because 1 over 0 squared would be undefined. So the graph never actually hits 0, but we can talk about what happens as it approaches it. And so here it's approaching infinity. It's going up towards infinity. And then the second part of this question asks, well, what happens as x approaches 0 from the right? So now if I come from the right and approach 0, I can see, well, it also is going up towards infinity from that direction as well. So how I might write the notation for this is f of x approaches infinity as x approaches 0 from the right and also from the left in that second line. So that's what that notation is describing. It takes a little while to get used to, so you want to kind of practice with kind of reading it out loud, maybe even translating it, writing down what this means, so you can kind of start to get a hang of the notation. Another way of asking this type of question, for the next part here, part B, what is the end behavior of the graph? So what happens at the ends of the x-axis as we go off to negative infinity and positive infinity on this graph is what they're asking. And so if I look here, well, as we go off to the right to positive infinity, this graph is approaching the x-axis. It's approaching 0. Never actually touches it because I can never take 1 and divide it by a number and get 0. I can get really darn close though. So f of x is approaching 0 as x approaches positive infinity to the right, and it's doing the same thing to the left. It's approaching 0 as well. So that's how end behavior and this arrow notation works when looking at rational functions. We end up with this kind of behavior happening a lot with rational functions because we're dividing two numbers. So we often end up with places where it's undefined, or there's numbers that are not part of the range. And so when we get these areas, these straight lines where it approaches but never actually hits, we call those asymptotes. A vertical asymptote is a vertical line that the graph approaches but never actually hits. So this is where f of x approaches either positive or negative infinity as x is approaching a particular value. So if we go back to that last graph, well, 0, x equals 0 is a vertical asymptote, right, which is the y-axis. It approaches it, but it never actually hits it. Now, if we're wondering, well, how do I find these, or when do they occur? It happens when the denominator equals 0, right? With the last one, 1 over x squared, when x squared equals 0, before we got our vertical asymptote, which was 0. So that's how you can actually find a vertical asymptote without having to look at the graph or pull out a calculator to graph it, is you can take that denominator, set it equal to 0, and solve. Another way of saying this, if we think back to polynomials, is the 0 of that denominator, the polynomial in the denominator usually, is going to be a vertical asymptote. X equals whatever that 0 is. So let's look at an example with this. So here I'm being asked to find all the vertical asymptotes of the function 2x over x plus 1. Don't care too much when it comes to vertical asymptotes about what's happening on the top. I really am going to focus on that denominator. So x plus 1, I want to set that equal to 0, and whatever x value I get from solving this equation is going to be my vertical asymptote. So, well, if I subtract 1 from both sides of that equation, I get a vertical asymptote at x equals negative 1. And sure enough, if I graph this function, and here I added a dotted line to the graph, you can see at x equals negative 1, the graph is approaching either infinity or negative infinity, depending on which side we're coming from, at negative 1. Okay, so they're not the only kind of asymptotes that we can run into. When we saw that first example, we also had a horizontal asymptote at 0. The x-axis, the graph was approaching it, but never actually hits it. So this happens when f of x approaches some value b as x goes to plus or minus infinity. So as we go to the right and to the left on the graph, what happens to the function? That's what we're looking at. That when we approach a line but never pass it or hit it, then that is a horizontal asymptote. So let's say I have some rational function. So I've got a polynomial p of x over a polynomial q of x. Find the horizontal asymptotes is a little bit more work. This is a nice thing to have in your notes to just reference because it's hard to memorize little details like this. But let's say the numerator has degree n and a leading coefficient of an. Okay, so that leading term, the number multiplying out front, is some value. We're going to call it an. And let's say the denominator has degree m and the leading coefficient is some number en. So depending on which degree is bigger will tell me where the horizontal asymptote appears on these. If the numerator's degree is smaller, then you'll have a horizontal asymptote at y equals 0. So as you go off to infinity and to the left and right, we're going to approach 0 if the degree on the top is smaller. If the degrees are equal, so maybe you have a quadratic over a quadratic, they're both x squared polynomials, then you take the leading coefficients and divide them, and that is where your horizontal asymptote will be if the degrees are the same. So it would be an over bn would be, whatever number you get from that, would be where the horizontal asymptote is. Right, so those are our first two options. That's how you get a horizontal asymptote. Either the degree of the top is smaller or they're equal. If the degree of the top is bigger than the degree of the bottom, then we have what we call a slant asymptote. So it's not vertical, it's not horizontal, it's something in between. It's some other line that is not vertical or horizontal. So this is what we call a slant asymptote. And that's when the degree of the top is bigger. And to find that, now we're looking for an equation that's a little more complicated. It's not y equals something. It's going to be y equals, x times something plus something. I'm going to do some polynomial long division to find that slant asymptote. So to find the slant asymptote, you divide your long division, p of x over q of x. You can use synthetic division if that applies, or long division if synthetic division does not work. All depends on what that denominator looks like. And so you do that long division, and the slant asymptote is the quotient without the remainder. So whatever remainder you might get from doing the division, you drop that off, and whatever equation is left, that is the equation of the slant asymptote. Okay, so let's take a look at that last example we did, 2x over x plus 1. We already found that we had a vertical asymptote at negative 1, because that's when the denominator is 0. Now let's see if we have any horizontal or slant asymptotes on this one. And you're only going to have, if you look at those options, you'll only have one or the other. You won't have a slant and a horizontal in any particular rational function. So here I look, the numerator is 2x, that's degree 1, and then the bottom, x is degree 1 as well. So the degrees are equal, which means that I have a horizontal asymptote. Right? And to get the equation for that horizontal asymptote, I divide their coefficients. So the coefficient of the top is 1, coefficient of the bottom, the coefficient of the top is 2, coefficient of the bottom is 1. And so the equation would be y equals 2 over 1, or 2. That's where my horizontal asymptote would be. And there is no slant asymptote for this one. And sure enough, if I graph it, you can see my vertical asymptote at -1, and then horizontal asymptote at 2. So that is how you can find all the asymptotes when they're vertical and horizontal. Let's look at another example. Here we want to find all the asymptotes for this equation. We've got f of x equals x minus 2 divided by 3 times x plus 5 times x minus 4. So I usually start with the verticals. Just take that denominator, set it equal to 0. Okay, so I have 3 times x plus 5 times x minus 4 equals 0. I can see just looking at that I'm going to have solutions at -5 and +4. So that means that this rational function has 2 vertical asymptotes, and they're going to be at -5 and 4. Next up, I want to look at horizontal and slant asymptotes. And so I'm looking at the degree of the polynomials. The degree of the top is 1. The degree of the bottom, if I multiply that out, I would get a quadratic, so that's a degree of 2. That means that the top is smaller than the bottom. So I'm going to have a horizontal asymptote at y equals 0 when that happens. I don't care about coefficients or anything like that because the top is smaller than the bottom. And if I sketch out that graph, and we'll look at more about graphing the rest of it later, but I at least have the asymptotes here in the function. Okay, the last thing we want to talk about today in this video is removable discontinuities. Now, something that we want to be careful with when you're looking for those horizontal and slant asymptotes is you want to make sure that you're dealing with a completely simplified quotient. So you don't have any repeating factors in the top and the bottom for all of that. If you do happen to have a polynomial that when you factor the top and bottom, you have a factor that cancels out, like let's say I have an x plus 1 on the top and an x plus 1 on the bottom, that would mean that there's a removable discontinuity there. Your graph's not going to pick up on this when you plug it in because it kind of automatically simplifies these things. So it's something you have to watch out for in your own technology. It's not necessarily going to help you out with identifying these. But it occurs when I have a common factor in top and bottom that would result in me getting 0 over 0 at a particular point on the graph. Now, even 0 cannot be divided by 0. So 0 divided by 0 is undefined. And so we call this a removable discontinuity. It ends up being a little hole in the graph where everything just kind of smoothly curves around it. But when I hit that one value where this happens, I get a little hole. So let's take a look at how to find that and what it looks like on the graph. So here I have the function x squared minus 9 over x squared minus 2x minus 3. Nothing's factored, so it's not obvious, where I have any of my possible asymptotes or if there's a removable discontinuity. So I'm going to factor everything completely. So the top factors into x plus 3 times x minus 1 because it's the difference of 2 squares. And the bottom factors into x minus 3 over x plus 1, or times x plus 1. So I can see that I have a common factor, x minus 3, shows up in the numerator and denominator. That means when I hit a value that causes those both to be 0, I get an undefined. This is a removable discontinuity. So when x minus 3 equals 0, which happens at x equals 3, I have a removable discontinuity. Okay, and I can see that if I just test it out, if I plug 3 into the function everywhere, I get 0 over 0, which is undefined. So when I sketch the graph of this is what a removable discontinuity looks like. At 3, I get a little hole at x equals 3, which turns out it's going to be 3 and 1.5, which I let the technology find that for me on this one. But that's what it looks like when you graph it. So I would go through the whole process of graphing this function and noting that I have a removable discontinuity at this point, and I just put a little hole at that spot so that we know that I can't really go through that particular spot. So that is how you deal with a removable discontinuity when you are graphing a rational function.